Good afternoon.
Hello. Hello.
Hi, Professor. Am I able to ask you a few questions before we begin class?
Real quick, we've got like 1 minute and 40 seconds.
I'm having a really hard time with the stereochemistry that I was emailing you about over the weekend.
Mm-hmm.
I'm just not understanding, I guess, how to turn it into a three-dimensional model from the two-dimensional thing we have. I'm not sure what goes on what side, really.
Well, the magic of that is that you don't have to draw it in 3 dimensions to understand it. My recommendation initially would be to watch the video. I will go over it, but not today.
Okay.
Yeah, I will go during the review session. If you want to organize a Zoom session with me, you're more than welcome to do so on an individual basis.
Sure, I'll email you.
Okay, thank you. Okay, that goes for anybody, not just Jonathan, by the way.
I thought I was special.
No, you're not. Sorry. Okay. Now, I was having a bit of difficulty making the PowerPoints come up, so I'm just going to be using the printable versions which come up here, and I know that those will be proper. So that was an issue I was having last time. Some of the diagrams weren't coming up properly. All right, today we're going to be talking about a competition between substitution elimination. Well, let's see where we're at in the course here. Make sure that everything's hunky-dory as far as the schedule goes here. All right, so we're looking at competition between substitution elimination is what we're looking at. And we'll get to an introduction of stereochemistry as well of SN1, SN2 reactions. So Wednesday is going to be a review. So definitely, Jonathan, I'll be going over stereochemistry again on Wednesday. There's no question of that. And then the test will be next, let's see, when is the test? Okay, the review, see, Monday, Wednesday.
Wednesday the 7th.
Wednesday the 7th is the test, yeah. So next Monday will be a review. So let's see as well. Well, okay, it looks like I've got 2 days set up here for review. But in reality, we probably won't get, well, we might get some of the stereochemistry stuff in today for the SN1, SN2, but that'll bleed into Wednesday. All right, but next Wednesday will be the test. So we'll have plenty of time to go over and review all the stuff we've learned for this test. I know there's a lot of material here, but it's actually not as bad as it seems, I don't think. Okay, so today we are looking at the competition between substitution elimination. Now, substitution is what we've been talking about. It is the substitution of a nucleophile for a leaving group. X is the leaving group, Y minus is the nucleophile. We talked about those definitions last time. Now, elimination occurs with the same substrates or the same reactants, but the products are different. If you look at elimination, the products are ones with double bonds in them. So substitution will be substituting. Elimination will lead to double bonds being formed in the products. There are 2 mechanisms that we talk about. These are not mechanisms you have to be aware of, but I'm just bringing them to your attention. There's an E2, which is of similar ilk to the SN2 in that it's one step. And it always involves the removal of a hydrogen and the removal of some sort of leaving group to leave a double bond in the structure. The E1 leaves the same double bond here, but you'll notice that's 2 steps as well with the formation of an intermediate carbocation, just like SN1 had. But we're not really that worried about the mechanism for these. All I really want you to be aware of is a pattern. And a pattern is fairly simple if you look at it. See, you've got the X group here, and then you remove the X group and you leave a double bond where the X group was. You can draw a double bond out to any C that has a hydrogen on it. I'll keep on saying that. Initially, you won't understand what I mean by that, but there's an H on this C. If there's no H on this C, then we cannot get a product there. But if we do have an H, then we can form a double bond out from where the X is to where the H was. And that's what we're seeing there. It's a very easy pattern once you get the hang of it. So when does elimination occur? When does substitution occur? Well, these are the conditions. This is not something you have to memorize. I actually give you this table on the test, and you won't have to memorize what these things do. But what happens is that if it's at room temperature and you're using a strong nucleophile, then substitution is favored. If it's a strong nucleophile, sorry, if it's a strong base and heat, then elimination is favored. And then if you've got combinations of the two, strong nucleophile and heat, strong base and room temperature, you'll find you'll get both substitution and elimination products. So what do I mean by a strong nucleophile? Well, strong nucleophiles tend to be things like S negative and N negative and CN negative. These will favor substitution. Strong bases tend to have O negatives in them. Usually they contain oxygen. And those tend to favor elimination. So if you look at the mechanisms here, or the mechanism for the elimination, you'll notice it always involves the removal of a hydrogen. Well, a hydrogen being removed means that it's being pulled off by something. So Y minus, instead of coming in and substituting for the X, is removing a hydrogen instead, which means it's a base and not a nucleophile. I'll say that again. A nucleophile will lead to substitution, the Y minus replacing the X. Y minus acting as a base means it's removing a hydrogen and forming a double bond that way. So that's what I mean by strong nucleophiles, strong bases. I'll
But
stop here for a second.
how do we know when we look at it that it's going to remove?
Because it'll be an O negative, Julie.
Oh,
Okay. Right. So anything with an O negative will act as a base. Anything that doesn't have an O in it will act as a nucleophile. Is that clear?
Okay.
Okay. Heat will favor elimination because elimination requires a higher activation energy than substitution, and room temperature will favor substitution for the same reason. So the reason that what I'm going to tell you that O negative tends to act more as a base than a nucleophile has to do with the concept of hard and soft charges. This is not something you have to be aware of for the test, but I'm just telling you this for a bit of extra information to give you a bit of context, because Julia, I know you had asked me, but this will give you at least a reason for why one acts as a nucleophile, one acts as a base. So in the case of things that are nucleophiles, they tend to have charges that can elongate, which is going to be more conducive to nucleophilic attack. So soft charges can tend to elongate and join together, and that's going to be favorable for substitution. Hard charges are very much more concentrated on the actual atoms themselves, like they are with hydrogen and the O minus because of the electronegativity of O minus. So the O minus is going to be a more concentrated charge. It will tend to react more with hydrogens rather than hydrogens adjacent to leaving groups rather than the actual leaving groups themselves. Then that will favor elimination. So that gives you at least a little bit of an idea. This is a very simplistic explanation of something that's actually very, very complicated. But that's that's as far as I'm willing to go into it. Does anybody have any questions so far? So what do you have to know? Well, you just have to know what a nucleophile looks like, what a base looks like. Bases are O negatives. That's really all you have to know. Everything else is going to be nucleophilic. All right, let's look at some examples. Now, I'm not interested in you learning any mechanisms for these. All I want you to know is what the patterns are. So looking at the top example here, what we do is we look at the reactants, and you see we've got SH negative and we've got room temperature. We look at the table, what we have is room temperature, and the SH negative is in this list of strong nucleophiles. Now there's a little bit of a wrinkle here. Oops, let me get rid of that. See if I can move this over a little bit. Here we go. All right. And the wrinkle is as follows. So we've got our compound. Let's try that again. Which has the Br on it, and it's being reacted with the SH negative and room temperature. So RT is just room temperature. So what we're expecting is that the SH negative will simply move in and replace the Br. The catch is that SH negative is actually better represented with the negative charge on the S. Now we understand that to be the case because if we were to draw a Lewis structure of SH negative, there's no way that you could have a negative on the hydrogen. Now why does this matter? Well, it matters because whatever has the negative charge is what joins on to the same location as where the bromine was. So that's all there is to it. That's substitution. Does anybody have any questions?
Yeah.
Yeah.
Is it always going to be the other element, not the H, because H only has one bond?
Yeah, pretty much.
Okay.
Now that's not the only example. I mean, let me throw something else at you here. I mean, I'm going to show you plenty more examples anyway, but let's say we had this situation. I mean, I'd want it to be clear that the S is the one that's going to be bonded to the C because it has a negative charge. Now, you know, you would never really draw this with the negative charge on the CH3, even though, you know, it'd be impossible for it to be that way. It would be much better to be drawing it in this way anyway, but SH negative's a lot like OH negative. Sort of everybody knows that the negative charge is on the S and not the H. All right, so anybody have any questions about the substitution pattern or understanding the substitution pattern? It pretty much is what it is. It's just substituting. That's what it says it is. Now, well, let's look at elimination. Now, again, I'm not that interested in mechanisms here. I'm just interested in patterns.
Are we gonna go over the mechanisms more in depth later?
Yeah, sort of more in test 3. We'll start doing, and in test 4 as well. But for now, we're not interested in the mechanisms. We're just interested in what the products look like. So this is going, because it's got an oxygen here, and we're looking at heat as well, then the situation is that we have a strong base and heat, which means that we're only dealing with elimination. The pattern, as you can see, will lead to a double bond, but the double bond could be on either side. Now, the rule that I tell you about here, and I'm going to put these in is that there are actual hydrogens here on the C's adjacent to the C with the bromine. And what we can do is we can draw a double bond out to either side of that. But the issue we're facing here is that since the starting material to bromine was symmetric, the two compounds we end up with are the same. So those two double bond compounds are identical, which means that only one of them is going to be needed to be shown.
In a situation where it wasn't symmetric, would you just do this molecule plus this other molecule? Okay.
That's exactly what you would do. It's exactly what you would do. So you can notice that the OMe minus never appears in the product. The reason for that is because what it's doing is taking one of these hydrogens and forcing the production of the double bond. So you'll notice that the base never makes an appearance as part of the compound. But what if you had something that was a strong base and say room temperature? Well, according to the chart here, strong base and room temperature would mean you'd get both substitution and elimination products. So what you would do is you would show, by way of answer, one would be the substitution product where the OMe minus replaces the Br, and the other one would be the elimination product. So you'll notice that the answer contains both of these. Obviously, it doesn't matter about the order, but you'll have an elimination product and a substitution product here. Does anybody have any questions so far?
So how can you tell which one to use during which circumstance?
Well, it'll be based on this table, which you'll have in front of you. So room temperature and a strong nucleophile will only lead to substitution products. Strong nucleophile and heat will lead to both. Strong base and room temperature will lead to both, and strong base and heat will lead to elimination.
Okay, and you said we'll have that table
Yes.
on the test, correct?
Yeah,
Okay.
that's correct. Yeah, you won't have
Thank
to
you.
memorize it. But what you will have to know, because I don't tell you this, is that a strong base contains O and a strong nucleophile doesn't.
Okay, gotcha.
The only thing, that's it. I mean, that's all. If you have to remember something, that's it. That's all you have to remember.
Could you show where example is not symmetrical, please? I didn't understand where to put the bond if, let's say, Br is not in the middle. What if it's on like the right side?
We will.
Oh, sorry.
Just hang on, Victoria. I promise.
I'm hanging on.
Hang on for dear life.
Sorry, I thought you were moving on, so I figured out.
Oh no. I've got to lay the groundwork first, and then we can get into the mechanisms. Sorry, not the mechanisms, the examples. Okay, so the other thing we have to be concerned about here are the most stable alkenes, and we can figure out which alkene is more stable by looking at something called the Zaitsev rule. Now, Zaitsev rules basically states, Victoria, can you confirm this for me? Do you speak Russian?
Yes.
Okay. Is Zaitsev carrot, or is that a big lie?
Come again?
Does Zaitsev mean carrot?
No, carrot is mорковь.
Oh, okay. So, all right. So whoever told me that is a liar. Anyway.
You're a liar. You have to hunt it down.
Somebody who told me they spoke Russian but really didn't. All right. Well, thank you. Now I'll never have to worry about that again.
Don't trust anybody.
All right. So the most stable alkene, basically what happens is the more carbons there are connected to a double bond, the more stable it is. So here's an example, and actually, Victoria, this is an example of one that is not symmetric. So you can see that if we pull the Br off, we can put a double bond out to any C that has a hydrogen on it. So this is a C out here. Can you all see my cursor or not?
Yeah.
Yes.
Yeah.
Okay, good. Okay, so there is a C at the end of this bond, and there's a C, of course, down here. There's also a C over here, but this C doesn't have hydrogens on it. So we can't draw a double bond out to that. Even if we did, we'd still end up with something that had 5 bonds. It'll look very silly. So we'd have 2 possible products here. One where the double bond can be drawn downwards, and one where the double bond can be drawn out to the C that's got the hydrogens. A lot of people don't remember that there's a C out here on the end. They seem to think it's a bond going out to nowhere, but it is. It's attached to a C. And that C has hydrogens on it. So we can draw a double bond out to that C and a double bond down to the C below. So we can have 2 possible products here. I'm going to draw them over here as well so we can count the number of carbons directly connected to the double bond. Now remember, we're not interested in the double bond carbons themselves. We're only interested in the C's directly connected to the double bond. So let's look at those, and I'm just going to line them in. So there's a C here, there's a C over here, and there's a C down here. So this one would have 3. The one next to it.
Could you show that again? I missed that.
Okay.
The 3.
Okay.
See?
I'm going to, there we go. All right, you ready?
Yep.
Okay, so there's a C here, there's a C here, and there's a C down here.
All connected to the double bond.
All connected to the double bond. So that's 3 by C's connected to the double bond, right?
I have a question.
Yeah.
In the example, where does the bromine go?
It's it comes off as a leaving group, just like it would in a substitution. So it comes off as Br negative. I haven't shown it because I'm not really interested in those products. We're only interested in the carbon products for these examples. Okay. You're welcome to include the Br as Br negative if you want to. It'll warm my heart to see it, but it won't make any difference to your grade. So let's look at the other one and count the number of carbons directly connected to that double bond. And I'm hoping that you can see that we'd have a C here connected to it and a C here, so that'd be 2 by C. So the Zaitsev rule, will only apply when we're comparing 2 compounds with double bonds, and we count the number of C's directly connected to the double bond, and that tells us how stable it's going to be. The more C's there are connected to the double bond, the more stable it is. And that means if you're forming just 2 compounds with double bonds and they have different numbers of C's, then the one that's more stable will be the one that I'm calling main or major.
Can you repeat that really quick? You said
the one with more C's will be the main one.
Okay.
Because it's more stable.
Okay.
Is that okay, Deanna?
Yes, I got it.
Okay. Is anybody uncertain about how to count the C's directly connected to the CC double bond?
I am. Can you just explain that one more time, please?
Okay, I'm going to just circle the double bond here. So we're not actually talking about the C's that are actually in the double bond. We're just looking at C's directly connected to the double bond. So I'll just put arrows to them here. And this one happens to have 3. There's also a hydrogen connected down here that I'm not showing, which I'm not going to show. And the other one has 2 C's directly connected to the double bond. Is that a bit more clear, Nora?
Yeah.
Okay, but the main point is that the more C's that are connected to the double bond, the more stable it is. All right, anybody else have any questions or any concerns about finding the C's that I'm talking about here?
Does it matter which C you use that's connected to it, or like could you use any of the other branching ones?
No, it has to be C's, only C's directly connected to the double bond. They're the only ones you can touch.
Oh, okay.
That's why I've been very careful to put arrows there and just show those specific C's, Sierra. That's it.
I got you.
All right, only C's directly connected to a double bond. All right, any other questions?
Dr. Musgrave?
Yeah.
I think I just want to comment on my little Russian lesson here. I think you mixed it up with it. Instead of saying carrot, you meant to say rabbit, rabbit's rule.
Oh, rabbit.
'Cause that's what it means.
Zaitsev is rabbit.
Yeah, sorry.
Oh, okay.
Yeah.
Well,
'Cause
maybe,
rabbit is fine.
maybe it was me who got it wrong. Carrots.
'Cause, I mean, they are
yeah,
connected to
they
each
are
other.
connected to each other.
Yeah.
Yes. All right. Thank you, Victoria. I appreciate the clarification. There we go. Zaitsev, rabbit. Okay.
Because the scientist's name is Zaitsev, so I think that's why they named it after him. Mhm.
Ah, yes. Not after rabbits.
No, that's his last name.
All right, so here's a more complicated example. And again, Victoria, you were asking about
Yes.
asymmetric ones, and this one is definitely a good example of that. So let's look at him. Okay, so looking at the things that we have OH minus and we have room temperature. So if we go back and we look at the table, remember you'll have this table, so you won't have to memorize it. We have strong base and room temperature. So we're expecting both substitution and elimination products out of this one. So let's look at the substitution one first. He's pretty easy. So the Br simply gets replaced with the OH, and the bond is, of course, through the oxygen in the exact location where the Br was. I'm going to stop here for a second. Does anybody have any difficulty with the substitution pattern for this reaction? Anybody have any questions? Now, what I'm going to do is I'm going to draw hydrogens off any C that's adjacent to the CBr bond. And by adjacent, I'm talking about next to the CBr. And you can see that the rule is that you can draw a double bond out to any C that has a hydrogen on it from where the bromine used to be. So you chop out the bromine and you can draw a double bond out to any of them. Now remember, the OH won't be in any of these products. So there's one. There's another one. And we have one out here. Oops. There we go. Does anybody have any questions about how I got any of those answers?
Totally.
Just the second one from the top.
This one here? The
Up
one
one more. Up one more.
This one?
Yeah.
Okay. So here's what we do. We just chop off the bromine, right? And we can draw a double bond out here, or here, or here. Any C that has a hydrogen that's adjacent to it can have a double bond. And this one that I'm pointing to with the arrow is the one you were talking about, Sierra. This one that I'm pointing with this arrow is this one here. And this one that I'm pointing with the arrow is the last one.
Okay, so when you do, what method is that again?
Elimination.
Okay, so when you do elimination, there's going to be 3 possibilities, basically?
Well, it depends on the symmetry.
Okay.
So, I mean, the answer is sometimes. It's the maximum, I'll tell you that. 3 would be the maximum you could have.
I got you. But if it was like not a
Well,
hexane, it would be a little bit different because you wouldn't have all of those attached.
Okay, can I show you another? Let me show you a competing example here.
Okay.
It's not the same thing, okay? What I'm drawing is not going to be the same thing.
I don't understand what the difference between this one and the last one that you drew. I drew them exactly the same way.
Julia, I'm not really understanding your question. Can you clarify? What
Okay,
you're-
so the last one you drew with the BR
Yeah.
had two adjacent Cs because, okay, so there's one line missing.
Yes.
That's the difference. There's
Yes.
one line missing.
Yes, that's
That
right.
could be an H.
Yes, that is an H.
Okay,
Yeah, that's the difference between those two.
okay. You looked so close that I was like,
Oh, I know. Devil's in the details, Julie. Devil's in the details. Now, I still haven't figured out the main on this one. I'll get to that in a second. Now, what I want you to see, Sierra, is that if I drew a double bond out here, or, whoops, or I did the other one, they'd be the same thing. Because the initial compound is symmetric down the center here. There's a plane of symmetry through there. So it would be the or there is important because you have to put either or of those, but either or one of those, either one or other of those. Otherwise, it would be wrong to include both. Is that
Gotcha.
fair enough?
Yeah, I get what you're saying now. Basically, you just don't want to be repeating anything like we were doing with line structures in previous test. I gotcha.
That's right. That's right. Okay, so back to this one here. Well, you know, if you're looking for a main here, there wouldn't be one because there's only one elimination product. So you wouldn't have to put main on anything. This one has 3 elimination products. And the one that would be most stable would be this one here that's got these 4 C's connected to the double bond. So I'd call this one the main. Does anybody have any questions?
So these double bonds are they're connected to the hydrogens.
Well, they're connected to well, sometimes they have hydrogens on them, but those are carbons that I'm pointing to right here. If I'll circle, I'll go ahead and circle.
Yeah, I see that. I was just wondering why never mind, I got it. Sorry.
Okay. Now the other ones, I'll point out the C's that are connected to the double bond here. That one has 3, and this one here has 2. So the one that has 4 connected to it, here's the main one. Anybody have any questions?
So whichever one is more stable, you're going to label as main.
Yep. Only if the alkenes though, Sierra. So you can only do that if there's more than one alkene formed.
Oh goodness. Okay.
Because I'm not
to be a circular,
Nope. Doesn't have to be.
so it works even if it's not.
Yep. Sure does. Sure does. Let's look at I have a little worksheet here.
As you go through the worksheet, can you include the mention of line of symmetry when it's applicable?
Of course I will.
Great, thank you.
You didn't even have to ask. I would have done it anyway. All right. Ignore that. I actually didn't create a quiz for this one. I toyed with the idea, but never did. Okay. No, hang on. No. Now what I'm looking for is actually in the blue book. Let's look at the blue book. As I said, this is all in the order of questions. It's a little bit easier to follow than the other one. All right, so that's question 5. This is question 6. So I've got these 10 examples here, and then after that, I've got about 35 other examples. All right. So there's plenty there for you to work through.
Thank you.
All right. More fun than a day at the fair, I can tell you that. Okay, so let's ignore number 1 because it's just a straight substitution. So looking at number 2, that one is symmetric.
Can you define line of symmetry?
Sure. A line of symmetry is a line that can be drawn through the compound or even part of the compound that has the same things on each side, also called a mirror plane. So that would be a line of symmetry through that compound.
So it's
How is
not
that
necessarily-
symmetry? Like if you were to fold it over that line,
Yes.
it's not going to match up with the other side.
Oh, hang on. Sorry, I put the line through the wrong place. Let me erase that. Sorry. Yes, you're right. Let's try that again. It is symmetric. I just put the line through the wrong place. How about this? Do you like this better? How's that? Is that more fun?
Yeah. Well, could you do it down the middle or no?
You mean down here?
And then fold it over left to right?
No, because you don't have an eye on that side.
Oh, I got you.
Right, you need it. It has to be the same. I mean, think of it this way. Think of it like this. And this is the mirror image that I'm pointing at here. So, it has to be exactly the same on both sides of the mirror.
Gotcha.
Otherwise, something's very wrong. Okay, so with that one, it's OH minus room temperature. As you can see, I've got the little table up here as well. OH minus, that's a strong base, room temperature. So we're going to get both substitution elimination. So the products for that one, we would have the I replaced with the OH, there's your substitution. And then the elimination could be one of two compounds. This one or, of course, the other one, which would have the double bond drawn downwards. Either one of those.
Okay, so why is it not both again?
Because they're the same.
I gotcha.
And they're the same. And the reason you know they're the same is because they came from something that had a plane of symmetry.
Okay, so if there's no symmetry, then you write down all the options. If there is, then don't write down the same.
That's exactly right. Yep. That's exactly right.
Would you want us to mark it as main?
In that case, no, because there's only one of them. You only have to do main if there's two or more alkenes formed. Different alkenes.
Okay.
Different alkenes. Otherwise, you can put main on there, but it's kind of doesn't really say that much. It's not wrong. You could say that. Yes, it's the main because it's the only. But that's like having one brother and saying, "Oh, he's my favorite brother," but he's your only brother.
That's actually an interesting question. Which one would happen more frequently, the elimination or substitution?
It varies because it depends on how hot we're talking. It depends on how strong the nucleophile is. So it's difficult to say, Jonathan.
Gotcha. Thank you.
So when you say plus, like when you say this, it can be this plus this.
Mm-hmm. It means you're getting both.
But does that mean you'll always get both, or it's
Yes.
really like an or?
No, it is no.
You will get both.
You will get both.
Okay.
It's a plus, yeah. But I guess what I'm saying is one of them can't be 0. It's not like a, I don't know. It's not really like an or. It's an and. All right, let's look at number 3. So that would be strong base and, sorry, was that strong base and heat for number 3. So that one is elimination only. But here's an example of one that's not a circle, right? So you get the double bond here and the double bond here. Oops. And you can clearly see those two things are different. But the reason we know that, and Sierra, this kind of goes to your question earlier, I can't draw a mirror plane through this. So I know that I'm going to have to get all the possible products here, which is really only 2 because it's only 2 carbons connected.
Is the plane of symmetry always going to be going through the like
Absolutely.
bromine or the iodine?
Yeah, absolutely. For true to C that has the leaving group, yes.
Okay.
Absolutely, that is true.
So which one would be the main alkene?
Out of those two, neither, because they both have 2 C's connected to the double bond.
Mm-hmm.
See that? So I wouldn't write main on either of them, or you could write main on both.
So what determines which one will form if neither one's preferred?
They'll just both form probably pretty much in equal amounts, Sierra.
Oh, okay.
Look at number 4. Now, does that have a plane of symmetry? Take a look at number 4. Sierra, I'm going to put you on the spot here. Do you think number 4 has a plane of symmetry?
Yes.
Well, it doesn't, because if you were to, again, try and draw a line through here, you'll notice there's no methyl group down here to match it with. So this one doesn't have a plane of symmetry. So again, this one is both substitution and elimination. Substitution's easy. It's just the SCH3 with the bond going through the S because the S had negative charge. And then you've got the other 2 products. And you see, when you draw those double bond products, you'll see why they're different. So this one has the double bond closer to the methyl group than the other one. You can see that makes them different. In this instance, again, that neither one of those is main because they both have 2 carbons connected. Or you can say they're both main or neither, doesn't really matter. All right, any questions about that?
Except for well, let's see, except for the OH negative. No, that's not true. Some of these have the negatives. If you're not sure which element, let me just say it this way. If you're not sure which element has the negative charge, what's the best way to figure it out?
You really, Rebecca, you'd have to draw a Lewis structure. Now for Cn minus, it actually turns out you draw a Lewis structure, it looks like this. So the negative's actually on the C for Cn minus. But definitely for something like OH minus, it's always on the O. Generally speaking though, I'm not going, except for Cn minus, generally speaking, you'll see the negative charge on the atom it belongs on. And for OH, things like OH minus, SH minus. Aside from those 3 things, I'd say that you're pretty much right with the negative charge being where it says it is.
Okay, thank you.
Okay. Any other questions? So like I said, I've got 35 examples here with answers as well. They all have answers on them with the mains marked as well. So, you've got a lot to look at and check yourself against. All right, let's take a squiz at a test question as well while we're at it. pull up one of these. Doesn't matter which. I'll do this one just for kicks. So we're looking at question 6 here. Here you go. See how you've got the table there in the test? So, you know, it's no real mystery there. And there's your questions here. All right, so I guess we'll go through it. Well, why don't you try it? Why don't you try it?
You made them all hard.
What's that?
So I noticed you made them all hard.
Really?
Well, it looks like that every single one of them has 2 different answers.
Okay. Well, I don't know if it makes it any harder though. Look, why don't you all give that a go? I'll give you a couple of minutes, see if you can come up with the products. Can you all see it? And you all got a clear enough view of it?
Yeah.
On the screen?
Yes.
Okay, good. Now I'm going to pull up my drawing pad here, but I'm not going to write anything down yet. I'm just getting it prepared. See, isn't that clever? I just put it right there and then I can put the products in.
I wish they had
Actually,
stencils.
it's actually not that clever. Oh, you know what? You can buy stencils, Sierra.
I should do that. Mine all look so wacky. I can't even tell what they are half the time.
Well, obviously you can't get. Well, I suppose you can even get stencils for the straight chain ones. But they're a little bit easier. But yeah, you can get stencils that allow you to draw hexagons and hexagons. You know, the worst ones to draw, Sierra, are the 7-membered rings.
It sounds terrible and something from Lord of the Rings.
Yes, that's right. One ring to rule them all. That's right. But the 7-membered rings are the worst ones to have to draw.
What about the 9s?
Oh, well, I don't know. Yeah, they're just as bad, I suppose. The 10s are easy though. The 10s aren't too bad. And the 8s are easy because they just look like stop signs. But the 7s, they're not so great. All right, let's take a look. So yeah, you're right, Julie. All of these need substitution and elimination products. Let's do the subby product on this one. First one. Whoops. Let me draw that a little bit more consistently with the other one. So there we go, it's better. So the substitution, now this is important. Again, it's OTBU. I wonder how many people, I'm not going to ask how many people did this, but I wonder how many people did TBUO like that. Anybody do that? Anybody want to admit to it? Okay.
I did OBUT.
Oh,
I just went backwards.
Well, no, that would be okay. What I'm looking for, Rebecca.
I wasn't sure.
What I'd be looking for, Rebecca, is definitely having that O connected to where the bromine was. That's what I'm most interested in.
Would you keep the dash between the T and the BU as well?
I would.
Okay, so it's O-T-BU.
Yeah, that's how I'd put it down. But it's definitely wrong to put TBUO because the bond is through the O and not the TBU.
What if you did OUB-T, like literally backwards?
No, I suppose I could live with it.
Because that's what I did.
Yeah, I could live with it. But I think Rebecca did the same thing. That's okay. All right, and there's one other product for that one. And that's this one here. That's it. Remember, you take off the BR and you can draw a double bond out to that C and that's it. So if you drew double bonds, if you drew products that had double bonds in the ring here, those would be wrong. Anybody have any questions?
So that was strong base room temp?
Yeah, strong base room temperature, that's right. Okay, B. Yeah, we'll get the substitution first. As I said, the negative charge is actually on the C. And the elimination product says 2 is this one. And this one. And I'm hoping you can see that this one would be the main out of those two. All right, any questions about B?
I had a quick question about A, and maybe it applies to B too, but with A, so you're taking the connection from the C to the BR off, and that leaves the C out there alone, and it's from that C that's off the ring, that's where the double bond comes back to the ring?
That's right.
Okay. Because I feel a little confused. Originally, I had drawn it with the double bond.
Inside the ring?
No, even more creative. Kind of take literally the letters BR off and do the double bond on that line.
Oh, okay. But you know, you got to take the whole thing off, including the bond.
Okay. Take the BR with its bond and leave the C alone.
Yeah.
And then from that one, work your way back to double bond to the C before it. Does that make sense?
The C adjacent to it. Yeah, the C adjacent to where the BR was connected.
Okay.
But you can only draw double bonds out to C atoms that have hydrogens on them.
Oh, okay.
Okay, I have a huge question about B though that you just did.
Okay.
You changed it.
All right. Yeah, okay. So all right. Okay.
You can't do that. It makes me cry.
Well, I'm sorry. You just got to toughen up.
I know, but then
Julie.
we said the other one was the main, and I don't even have that one drawn. I'm like, I don't know which one is the main now.
Well, the main is the one that's got 2 C's connected to the double bond.
Okay.
And this one only has 1 C directly connected to the double bond. Now, Julie's complaint is that I changed the shape of it. She thinks I should have drawn it like that. But it's the same thing.
No, but it's flipped upside down.
Who cares?
I can't visualize it when it's flipped upside down.
Well, you're going to have to learn.
I can't even read a map.
I also have a question about B.
Yes.
Would it have been incorrect to draw the CN as instead like another bond, another triple bond connected to the nitrogen?
You can
Like
do
instead
that if you want to. That's fine. C
Okay.
triple bond N, that's okay. But it's understood there has to be a triple bond there. Otherwise, there's no way that could exist.
Right.
Because carbon needs 4 bonds, right?
I
So-
meant like, you know, instead of drawing out the letter C and keeping it a line structure.
Oh, if you wanted to.
Okay, it wouldn't be wrong. That's just
No, it wouldn't be wrong. But look, if you're going to do that, then do it right. Do it right, Jonathan,
keep it straight.
and keep it straight. Right?
I have a question, since
Yes.
I can't always tell just by looking yet which C's have H's and which don't. Is there a possibility that we're going to have to realize that we may not be able to form these?
Possible, yeah.
Okay, so so
Okay.
for a person like me, should I go through and make sure there are H's on these C's before I just start adding double bonds willy-nilly?
There's an easy way of doing that. These are all line structures, Rebecca.
Okay.
So as long as a point doesn't have 4 lines coming off it, you're in business.
Okay. All right. But I should double check that first
Yeah, well,
before I
yeah.
add the double bonds.
Yeah, the rule is this. I mean, when you're drawing a line structure, anything with a line out to it is to a C, and anything that's needed to bring it up to 4 bonds is going to be a hydrogen.
Right. Okay. I'm just saying, I haven't looked at these for my whole life. And so it's not always readily apparent. Like I actually have to still sit and think and count to
Well,
make
that's
sure.
okay. That's okay.
Okay.
So as long as you get it right in the end, right?
Exactly.
So for C, that would be the substitution product. And this one would actually end up having 3 elimination products. I did that just to annoy you, Julie. I drew that in the opposite direction.
Thank you. Very mean.
Huh?
You're a very mean person.
I am. I can be.
No, I don't know if I got it right or not.
Oh, well. Oops. There we go. And the main one would be this one. Because it's got 4 C's connected to a double bond.
Because S has a negative charge, should we put it on the one that you in the C example? I don't know if I asked this correctly. In the example A, there's we put a O negative T
Mm-hmm.
and should it be a negative on the C example? You know,
Not in the product, not in the product, Victoria. Oh, but you're saying when it's drawn?
Yeah.
No, well, I mean, it's really like that, but you don't have to draw it that way.
So if you go up in example A where you drew it, there's O negative T B.
Oh, no, that's not a negative. It's a
bond. It's a dash. I'm sorry.
And actually, that shouldn't be. No, that's a T, by the way.
Oh,
let me redraw that. I'm going to redraw it. Okay, give me a second. It wasn't wrong. It was just not clear. Okay.
Sorry, that's where my confusion came from.
Let me erase that. Okay, let me make that a little bit clearer. All right. So that's not a negative, that's a bond, right, to a TBU.
My bad.
Is that all right?
Yep.
Are there addition signs between each of the structures?
Yes.
Like on B and C? Yeah.
Yeah,
okay.
there are. Yeah. Right. You're right. There we go. And on this one too. If you don't include the addition signs, I won't be too upset.
So that last one at the bottom right, that's going to be a double bond off of that chain, correct?
Off the ring, you mean?
Yeah, off the ring. Mm-hmm.
Yeah, that's right.
A double bond. Okay.
Mm-hmm. All right. Any other questions about this one? Okay. All right. I'll leave that up. We'll see. We may or may not get to looking at a test question that involves the other topic, but we'll see. All right, let's see where we're at here. PowerPoint. There we go. Okay. So looking here at stereochemistry of nucleophilic substitutions, I'm going to show you a video. Actually, I'm going to pull up video, which means I'm going to have to share this probably. There we go. All right. And here we go. This mini lecture serves as an introduction to the stereochemistry of nucleophilic substitutions. Now, I know we've seen this before, but it's useful tool for allowing us to see the differences between SN1 and SN2 substitutions and the stereochemistries of their products. So let's look at SN2 first. Again, we've got our illustration of the backside attack and the inversion of the stereochemistry. We'll see a bit more of that in a second. Now watch as we know that the nucleophile comes in, attacks from the back, and twists the compound so that it's like an umbrella on a windy day. It turns inside out. Now you can see that what's going to happen when this comes in and attacks from the back, the product we get, and it'll be a single product, will be the exact opposite stereochemistry to what we started with. So there you go. The product looks like this and the reactant looks like this. If you had a mirror down the front here, you can see they're basically like enantiomers. They're not really enantiomers because these two things are different, but they're like enantiomers. The point being they do have opposite stereochemistries. If we started with an S reactant, we'd end up with an R product. If we started with an R reactant, we'd end up with an S product. Now let's look at the SN1 reaction. In the first step of an SN1 reaction, the leaving group... So I'll go back to the... I'll just stop here for a second. Did anybody have any questions about the SN2 at this point? Okay, so the SN2, what happens is that there is inversion of stereochemistry. You start with R, you end up with S. You start with S, you end up with R. It's only a single product. It leaves, leaving this planar carbocation. Nucleophile can attack from this side or from this side. This leads to a 50-50 chance that we could get either product, which leads to two possible products being gained by this reaction. And these two products are mirror images of each other and are thus enantiomers when this was a chiral center. So if you started off with an R reactant, you would get an R plus S product. If you started with an S reactant, you would end up with an R plus S product. Leave it there for now. Okay, so that's the bottom line there. Whoops, start again, sorry. No, okay. So there, that's the summary there. SN2 leads to inversion of stereochemistry, whereas SN1 leads to a racemic mixture, 50% R and 50% S. So R gives R plus S and S gives R plus S. Does anybody have any questions so far? All right, so here's my example, or here's an example of a test question. Draw and name the products and starting materials of the following, and I always tell you what it is if it's SN2 or SN1, and ask you to include all the stereochemistry. So I think this is the easiest way of doing it. You may not like doing it this way. There's millions of ways to skin a cat. This is just one of them, but I think it's the easiest way of doing it. So you've got to remember that with SN2, we're getting a single product, and that single product will be an inverted version of the reactant. So the first thing we do is we look at the compound itself and we determine, well, we try and determine what the priorities are so we can identify the lowest priority group. In this one, it's pretty clear the hydrogen is going to be the lowest priority group. I'm not really interested in anything else right now. I just want to know which one has the lowest priority. I also know that the hydrogen's in the wrong place. It needs to be in the back. So it needs to be where the BR is. So when I'm doing the answer to this, I know it's going to be a single product, and I know it's going to be the opposite stereoisomer to what's here. Now, I can't look at this and tell you if it's R or S because the hydrogen is sticking out here. I could try and draw this in such a way that puts the hydrogen into the back, but I don't have to do this. I can actually kill two birds with one stone and invert this and substitute it at the same time. So I know that the H needs to be where the Br is. So what I do is I switch the H with the Br and then I switch the Br with the I, knowing that the product is a substitution process. By doing this switch, I'm actually inverting the stereochemistry. I'll say that again. By doing this switch, by switching the H with the Br in the first place, let me get my pad here. See, if I was doing this without stereochemistry, I know that the product would be that. The I would replace the Br. But based on what I've just told you, I know that the product actually inverts stereochemistry. So if I was not to replace this with Br first, let's just go ahead and put the Br where the H is. What I want you to believe is that this has the opposite configuration to the one we started with, because what I did there was simply switch two groups. And whenever I switch two groups, that reverses the configuration. The other thing I do here is I actually then go ahead and replace the Br with the I, because it is a substitution process. So that's what the product looks like.
So you substitute the Br with I instead of sodium because they have the same kind of charge?
Well, sodium, if you look at it, is going to be Na plus and I minus, right?
Correct. That, and Br is a minus, so that's why you use
Right. And
iodine.
this would be a spectator.
Okay.
It'll be there at the beginning and there at the ends. So you're just interested in the I part.
Thank you.
Now,
Okay, so I totally don't understand anything you just said, but is it safe to say that you're switching the stereochemistry by switching them and then just replacing it? I mean, is that
that's
like
exactly right. That's exactly what I'm doing. So for someone who didn't understand anything, you did a pretty good job of summarizing what I just said.
Okay.
No, Julie, that's exactly right. That's
Well,
exactly
I don't
what happened.
understand why, but I'm always willing to take your word for it.
Well, we talked about this whole concept of switching two groups and reversing the stereochemistry before. So that's the answer. I can say plus Br minus, but I'm not really that interested in that. I'm only interested in what's going on here in the product. So now that the hydrogen is in the back, I can actually figure out what the priorities are. So that'll be 1, that'll be 2, and that'll be 3. And this would be R. All right, so that's R.
How do we know that Na is a spectator?
Well, it'll be there at the beginning, it'll be there at the end.
I mean, when we see it like this, like you give us this example and there's that Na there, how do we like say, oh, well, Na is just a spectator? How do we know that?
Because it's got a positive charge on it and there's nothing there in that compound to react with positive charges. The only thing that can react with anything is that I minus.
But it doesn't say I minus, it just says NaI.
Right, but well, you would have to know that it is Na plus I minus. Just like
It's an
sodium.
ionic compound, just like every halogen with sodium.
Yeah, like sodium chloride, NaCl is Na plus and Cl minus. Yeah, you'd have to know that.
How would you know that?
I would have hoped that after 3 years of chemistry, you would. I'm sorry, Julie, but that's it. I have to be blunt about that.
That's okay. It's just that my last chemistry was in 1978. It's okay. Thank you.
So if we know that that's R, it means that this must be S. Ooh, gee, that's an interesting jump of logic, isn't it? How did I do that? Well, I know that in order to get to the product, I switched two groups, which meant I must have reversed the stereochemistry. So I've kind of using the stereochemistry of the product to deduce the stereochemistry of the reactant. Anybody got any questions? So the names of them would be, for the product, it'd be R2-iodobutane, and for the so it's a product, R2-iodobutane, for the reactant, S2-bromobutane. Those would be the names right there. But the thing I'm trying to focus on here is just how do you get the stereochemistries. Anybody have any questions? I can't believe nobody had any questions.
You said the product was S.
I'm sorry? No, the
You said
product
the
is
product
R.
was S.
The products are, the reactant is S. Deanna?
Okay.
Wait, so how would we answer the question? Like, is it just asking us to do the replacement, or is it asking for the S and R assignments?
Both. It says draw and name the products and starting materials of the following SN2 reaction. Include all stereochemistry. So you have to draw and name. So this is the answer here. So R2-iodobutane and S2-bromobutane, and of course the actual stereochemistry drawn of the product.
Okay, I got you.
Okay. And another example, this is the SN1 example. Here's what I would do with that. I think it's a little bit easier, actually, the SN1. Here's what I like to do with the SN1. I know it's going to be a substitution. So what I do is this for the products. The first one I draw is just going to be a direct substitution without changing the stereochemistry. Remember this, R gives R plus S. So you're going to get both. S gives R plus S. This is for SN1. So that's a direct replacement. And this would be an inverted replacement. So I just switch the I and the H here. So that the lowest, oops, sorry about that. So the lowest priority group goes into the back. So the I and the H. There we go. So that's inverted. And I always arrange it so that the lowest priority group goes in the back. And then I can do the stereochemistry on the one that I have that has the lowest priority group in the back. And that one would be, you can see over here, R2-iodobutane would be this one, the inverted one, so VR. And this one has to be S because they have to be opposite. And since this came from a direct replacement of the bromine, then this had to be S as well. So does anybody have any questions?
So when you're assigning priorities, you said the one in the back is going to be the lowest. Do you start one where whichever one's in the front? Is that what you assign as first priority?
No, it's whatever has the highest atomic number, atomic mass.
Oh, yes. Okay.
So I, C, and C.
Mm-hmm.
Now, out of those, you can't get a winner yet, but this C has a C attached to it, number 2, whereas number 3 has an H attached to it. So the number 2 is the winner.
I gotcha.
Those
Thank
two.
you.
That's how we get this. That's how we get them. All right. Well, we'll leave it there for the day, and I will do more of these examples at the beginning of the next class, and then we'll start on review for the test. All right. Does anybody have any questions? Last questions here.
I have one.
Mm-hmm.
Why is it R2 I do butane and not I1 because the high priority is the iodine?
Because when I talk about the 2 there, it's the position in the chain, Nora, not the priorities.
Okay, I get it.
1, 2, 3, 4. Yeah, that's something that's remember that's two different kettles of fish. The priorities in versus the numbering on the chain.
Okay.
Okay. Any other questions?
There's one in the chat.
Okay, let me see if I can pull this up. Okay, very, very quickly, assignment of priority. So looking at this, I is 1, and then it's C and C. And because I can't get a priority based on just C and C, what I do is I ask myself, what's the heaviest atom attached to each of these? The heaviest atom attached to the C on the left is another C. The heaviest atom attached to the C on the right is an H. So the one that's got the C connected wins versus the one that's got the H. So that's how I know it's 1, 2, 3. Okay. All right, we'll leave it there. If anybody wants to hang around and ask me questions, they may. And for everybody else, I'll see you Wednesday.
Yeah.
Thank you.
Thank you.
Thanks.
Dr. Musgrave.
Yeah.
While you have my courses pulled up, can you pull up the test key for fall 2017? Because I'm confused on the priority numbering. Like, I feel like I did it right, but it doesn't make sense.
Okay, fall 2017. It could just be drawn differently.
Like, I got the same drawing, but my priority was like opposite of theirs.
Oh, okay. Well, let's have a look.
Okay.
Hopefully, I hope the key's right. I hope you're wrong.
Yeah. In part, I do too.
Fall 2017 key.
Yeah.
Let's take a squeeze.
So for number 8.
Okay.
Is it 2017? That's so weird. Okay. Wait. Okay. So yeah, wouldn't the 1 be on the CL and then 2 be on like the wedge kind of thing? Or like.
Yeah.
So it would go CL that
1,
and then the H.
2. No, you can ignore the H, Courtney.
Ooh. Okay.
All right. I think that's where you're making the mistake. You don't count the 4 at all. 1, 2,
Yeah.
3.
Oh, so don't like disregard having the H there at all. Just look at the other
Yes, that's right. You disregard the lowest priority group.
Okay, that makes a lot more sense. Is that true for like
Everything.
all of it? Okay, perfect.
Everything.
All right. That sounds okay. That's a lot easier. I was trying to figure out what the fork because I was like, that's like a zigzag kind of star thing. So I was like, that doesn't make sense.
Yeah.
All right, that seems simple now.
Okay, good.
Sorry.
That's
Thank
all right.
you.
No worries, Courtney.
See you Wednesday.
Bye, Courtney.
Bye.
All right.